we're going to continue with our probabilities here. This is 11-3 day 2. Something we're going to talk about today is the difference between independent and dependent events. Dependent event, you can kind of hear in the name, but it depends on the occurrence of one other event. In other words, its probability is affected by another thing. Independent is the probabilities are unaffected by something else occurring. So we'll get into that in just a second a little bit more. Something we're going to talk a little bit more about too is the and versus or. So if we were looking at this, you draw a card from a standard deck, which is more likely. So it is a king or a heart. So that means I could draw a king, a heart, or it could be a king of hearts, which is, sorry, I'm going to write or in there, or both. So there are lots of chances for success, okay? Because I could be king, heart, or both. So lots of chances for success. Okay, so because of that, this one is much more likely. If I want it as a king and a heart, that means it's a king and heart at the same time. So my only option is the king of hearts. So this one is much harder to succeed, okay? So when I think about when I want to calculate these probabilities, when we were doing the or, we were doing it's more open, which means it's more likely. There's more options. Okay, and means it's going to be less open or less likely. So I'm going to say more specific. So it's less likely. Okay, so because of that, that affects how we calculate the probability. So let's look at this. We did the addition rule in our last video. So which one is more likely? So let's just calculate these. If I were to do a fourth plus a fourth, I would get 2/4 or 1/2. If I were to calculate 1/4 times 1/4, I would get 1/16. 1/2 is way more likely than 1/16. So this goes with or, and this goes with and, because it is way less likely. So anytime I have an and probability, we are going to use a multiplication rule instead of an addition rule, okay? And we're going to look at what's the difference between my multiplication rule when I have independent versus dependent. So this is where we're going to get into that. I'm just going to write the formulas and then we'll do some examples. So, and I use my intersection. So if I want the probability of the two events, their intersection, the and, how I calculate that is I'm just going to do the probability of A times the probability of B. Pretty simple. So just like this, multiplying the two probabilities together. When it's a dependent event, it's the same exact thing, but we're going to do the probability of A times the probability of A given B. Or sorry, B given A, I said that backwards. B given A has already happened. Okay, and we're going to see an example of kind of the difference between these two here. Okay, so we have in a bag 9 red marbles, 3 green, and 4 yellow. So what's the probability that we draw red, then green? So this is an and because there's only one situation where we draw red first and then green. Okay, there's not red or green. It's red, then green. That is the only option. So this is an and, okay? And because not red or green, but one scenario, so not super likely, of red, then green. So very specific. Okay, so specific goes with and. Okay, so how I'm going to do this is I want the probability of red times the probability of green. So we're using this, okay? Probability of red, probability of green. Because my probability of green does not change, because this is with replacement. So I draw one marble and I put it back in, okay? So the probability of red times the probability of green. So my probability of red, so total I have 12, 16 marbles. So there are 9 of the 16 are red. and 3 of the 16 are green. Okay, so 9 times 3 gives me 27 over 256, which, if I put that as a decimal, is about 0.105. Okay, so that is my probability of drawing red, then green, that specific order. Okay, so now, same thing, but without replacement. So that means I draw one and I keep it out, okay? So this is going to be probability of red, still that, but this time I want to know what's the probability of green given a red has been drawn, okay? Or given that probability has occurred. So in this one, this is still 9 out of 16. But this one, so if one has already been drawn, there's only 15 left. So this is now 3 out of 15. Okay, so if I drew a red, now I only have 15 to choose from, 3 of those being green. So this changes the probability just a little bit. 16 times 15 is 240. So if I do that division, it's about 0.1125. So this one's a little bit more likely, but this is an example of a dependent event. Okay, and this one would be independent. So without replacement is dependent because my probability depended on what happened on that first one. Taking a marble out affected the probability, so that was dependent. Here I put the marble back in. The probability of drawing one color over the other does not affect anything. Okay, sorry, wrong one. Okay, tree diagram. You guys have seen a little bit of this before, but actually maybe this is not. Sorry, I haven't really done much. We did a little bit with the boy, girl back in the beginning, but we're gonna do a little bit more. So here I have box 1 contains 2 red marbles and 1 blue marble. Box 2 contains 3 blue and 1 red. Okay. If you randomly select a box and then randomly select a marble, what is the probability it's red? Okay, so we are going to say I have a 50% chance of choosing box 1 versus box 2. So I have 1/2. I could choose box 1 or box 2. Then within that, sorry, I got some stuff on here. Okay, then within box 1, there are 2 reds and 1 blue. So 2 out of 3 for red, and 1 out of the 3 for blue. So in this one, the probability of box 1 and red is 1/2 times 2/3, okay, which is 1/3. Okay, here I have 1/2 times 1/3, which is 1/6. Now box 2, okay, we have 3 blue and 1 red. So there's total 4 marbles. So we have 1 out of the 4 for red and 3 out of the 4 for blue. So those probabilities, I choose box 2, so 1/2 and 1/4 is red. So 1/8. Blue, we have 1/2 and 3/4 if I were to choose box 2 and blue. Oh, sorry, 1/2. Do it in the same order here. Okay, which is 3/8. Okay, so we wanted what is the probability of red. So this is box 1 and red. So there's a red. This is box 2 and red. Okay, so it could be box 1 or box 2. So because I just said the word or, this is add, right? So the probability of box 1 and red is 1/3. The probability of box 2 and red is 1/8. So if I got a common denominator, this would be what? 8/24 plus 3/24. So 11/24 would be the probability of me choosing a red marble out of either box. Okay, this is actually a really famous probability problem. Probably rings a bell with a lot of vaccinations being talked about, but this is a medical test for a certain disease, and it's 98% accurate. Sounds super good. The CDC estimates about 1% of the population actually has the disease. You have taken the test and tested positive. What is the probability that you actually have it? Okay, so we're actually going to do the same thing. We're going to do a tree diagram. Okay, so we have the probability that you have it, okay, and the probability that you don't. Okay, so this is where 1% of the population actually has the disease, so 0.01, okay? 99% of the population does not have the disease, okay? Now, we have a test. So if you have it and you test positive, and you have it and test negative, those are our two options. Well, if this test is 98% accurate, then 98% of people who have it will test positive. Okay, of the people who have it and test negative, there is that 2% that could be inaccurate, so 0.02. Okay, all right, so again, I can calculate these. So I have 0.001 times 0.98, which is 0.0098. So this is, you have it and test positive. Okay, this one, 0.01 times 0.02, and that is 0.1230. Okay, so this is you have it but tested negative. Okay, all right, so then there's the people who don't have the disease but still maybe get tested. So those who test positive, again, it's 98% accurate, but there are 2% that would be inaccurate. Okay, so don't have it, test positive. Oh, sorry, let me switch those. If you don't have it and test positive, that's a false result, right? So that's falling in that 2% of inaccurate. If you don't have it and test negative, as you should, that falls within that 98% that is correct. Okay, so then we calculate those. So this is 0.99 times 0.02, which equals 0.0198. So this is you don't have it but tested positive. Okay, this probability, 0.99 times 0.98, pretty high here, 0.9702. So this one is you don't have it and you tested negative. So we want to know what's the probability that you actually have the disease. You have taken the test and tested positive. So these are the ones that tested positive, right? Positive, positive. So if you test positive, we're going to do, we want the probability that you have it given you tested positive. Okay, so the probability you have it is have and positive over total positives. Okay, so have and positive is this probability right here, 0.0098. Okay, total positive is going to be this plus this. So 0098 plus, 00198. Okay, so if I divide those, we get 0.331. So that means we have a 33% chance that I actually have the disease. So I tested positive. There's only a 33% chance that you actually have the disease, which sounds crazy because it's 98% accurate. But because of all those different options between having it positive, having it negative, etc., there's actually only a 33% chance that I actually have the disease. So what should you do to verify is get tested again. So if you get the same result, then you're now at a 66% chance. You can add those probabilities together. So the more you test and get the same result, it continues to add that probability on top of itself, okay? So I'm just gonna add that in here. 2 tests with same result. So in this case, 33% plus 33% equals 66%. So your chances that you actually have it went way up if you have multiple tests with the same result. So one test really isn't super accurate, especially if you actually have it. So if you don't have it, it's a lot more likely, because look how high this percentage is. So if you get a negative test and don't have it, that is far more likely than if you get a positive test and have it. Okay, that's it for this video. Thanks for watching.